Okay, in this video we're going to talk about RTL, interconnects buses, and we'll do a hardware design example. In 133 we learned about a lot of important digital design principles and strategies and built a variety of combinational as well as sequential circuits, specifically synchronous sequential circuits from bits and gates. As we scale up the systems that we'd like to build and their complexity and the amount of logic they require, it's useful to have a slightly higher abstraction to describe these digital circuits. And this is where RTL, or the register transfer level, or sometimes called the register transfer language, comes in. It's a way that we can express our digital circuits, specifically synchronous sequential circuits, and how data flows through the circuit and is transferred between registers. So let's just jump into an example. Let's say that I wanted to implement the following logic. I have three registers, R0, R1, and R2, and if a control signal S1 is 1, then I'm going to transfer the data from R1 to R0. This is what this first line is saying here. R1 gets put into R0 if this condition holds. This is a basic operation in RTL, transferring the register contents. And note that it's also implied that this happens on a clock edge because this is a synchronous sequential circuit. If S1 is not 1 and if S2 is 1, then we're going to transfer R2 to 0 to R0 instead. Now in RTL, we can also express this more compactly as follows. So the signal, the variable before the colon, is what determines if the following RTL statement occurs or not. So in this case, if S1 is 1, then register R1 is transferred to R0. If S1 is 0, then the contents of R0 and R1 are maintained. However, in this case, I'm also going to do something else at the same time, and so I have a comma and another RTL statement. So I'm saying if S1 is 0 and S2 is 1, then R2 gets R0, which is the same logic that we've just described above. So the circuit for this would have three registers. And depending on the control signals, S1 and S2, I'll transfer one of these two registers, R1 and R2, into the register R0. And we've also seen a good combinational block that we can use for that called a mux. And in this case, if I assume that my registers are 4-bit values, I'm actually going to have 4 2-to-1 muxes, or one, we sometimes call this a quad mux. And in the case of digital components, we're also going to want to label the inputs, and especially for our muxes, which lines correspond to 1 and 0. Now to create this, I'm going to connect to the select line the control signal S1. So if S1 is 1, then it will connect the value of R1 into R0. If it's 0, then it's connect R2, and this value will flow to the input to the register R0. However, I also only want to transfer when one of those control signals is actually 1. So to do this, what I'll create is an OR gate that is as the inputs S1 and S2 into the load signal for the register R0. In this case, R1 and R2 are not changing, so I'm not even going to list the load signals. Okay, now with RTL, there's some standard notation. In general, registers could be any combination of characters. Usually we use the letter R and then a number or some letters, but we also can have special registers like PC or IR or SP, and we'll see these more as the quarter goes on. The key operation when we're working with the RTL abstraction level is the actual data transfer, and we symbolize that with an arrow. We can also transfer just certain bits. In HDL, we call this bit slicing, where I have a brackets and then the particular bits of a register that I'd like to transfer, or sometimes we might see a parentheses for single bits as well. We also use brackets for signifying when we're taking bits from a memory at a certain address. So if I wanted to get the contents of the memory at the address AR, and then I'm putting this into register DR. Now I can also do multiple RT operations at the same time and signify this with a comma specifying different simultaneous transfers. In RTL, I can also express many other slightly higher level operations as well, like arithmetic, logic, and shifting type operations. And all of these, as you would expect, are directly related to the logic that we also built in 133. So this first one is adding two registers, which could be implemented, for example, with an RCA as we built in 133. Taking 2's complement, we invert all the bits and then add 1, put that result into register X, subtraction, bitwise operations, logical operations, and OR, and so forth, and then shifting. If I needed to shift the bits one position to the left, I could do something like this. Okay, so now let's talk a little bit about buses and how we interconnect registers. There are a variety of strategies we could use for interconnects with some important trade-offs between them. So on the bottom here, we see that we have 8 registers. And on the left, I could choose to connect wires, and then we call this point-to-point connections between each of these. The advantage for this is that now in any clock cycle, I can transfer data from any 2 registers and multiple data transfers at the same time. The disadvantage is I have a lot of wires and a lot more logic. Versus on the right, instead what I could do is I could use 2 buses and share the interconnects for these buses between the different registers, resulting in less area, power, and wires for connecting each of these devices, but then also limiting the amount of parallelism and the types of data transfers I can do within a given clock cycle. So let's see an example of this. If I had 4 registers, shown here R0 to R3, I can have point-to-point connections between each of these. So I'm going to have a mux, a 4-to-1 mux specifically, that feeds in the input for each of these registers. And the inputs, the 4 inputs in each of these registers are one of the 4 registers. So if I wanted to execute these following RTL operations in one clock cycle, I can do that. So R1 can be transferred to R0 by simply setting the select lines for R0 to take register 1 and then setting the load signal high. And the same thing for register R3, I'll set the load signal to high and select register 2 coming into it. I could also just use a single bus. So this wire connecting the inputs to each of the registers could be shared, and then just have a single mux that selects one of these register values to be driven or put into each of the registers. So now if I would like to do the same 2 RTL operations, I can, but it's going to take me 2 clock cycles, because the first clock cycle I can do one transfer and transfer R1 to R0, set up the mux and the load signal accordingly, shown here in state X, and then in the clock cycle I would do the other. So this is the key point then, that a shared bus and its associated mux, it's a critical resource that you can only use to transfer one piece of data at the same time. The plus side is that with that single bus though, I can also still broadcast simultaneously to multiple destination registers. So if I wanted to write register R1 to several other registers, I could do that in one clock cycle. I'll leave the exercise of figuring out how to swap registers as an exercise for you, including with this first hardware assignment, implementing sorting to figure that one out. One more quick note here. We can also create, as we said earlier, buses. Instead of using multiplexers, we can also use tri-state devices. This is an example of the single bus case where we had, instead of 1 mux, we have 4 tri-state devices. So here's a single bus that comes into the inputs for each of the registers. And then we have tri-state devices that are enabled based on a decoder, where the input to the decoder are those 2 input select lines. And in this case, this will guarantee that we have only one of these tri-state devices driving the bus at a given time. This is an important aspect to make sure that you design correctly when you have buses and using tri-state devices, that you have only one device driving the bus or connected to the bus to the tri-state at a given time. Otherwise, this is when you'll likely start to see things smoking or damaging your internal circuits with too much current flowing. Okay, so now let's do an example of a hardware design using RTL. So let's say I wanted to multiply 2 unsigned numbers, and I want to design this circuit that had 2 n-bit numbers. So for example, if I wanted to multiply 7 times 6, we can do multiplication in binary just as we do multiplication in decimal. I look at the first bit of the multiplier and multiply that times the multiplicand. In this case, it's 0, so I have 3 zeros. And then I'm going to move on to the next bit in the multiplier and insert a 0 in the least significant position. Now I have 1 times 7, so this will be 1, 1, 1. Then I'll insert 2 zeros in the least significant bit positions. Again, do the same thing. I have 1 times 7, and so I'll have 1, 1, 1. And then I'll add up all these partial products to get the final result. In this case, I'll get 1, 0, 1, 0, 1, 0, which in binary is 32 plus 8 plus 2, 42 in decimal, which checks out because my numbers were 7 times 6. Now, for 2 n-bit numbers, at most, the result, you do the math, is going to be the largest the value will fit into 2 to the n bits. There are different ways that you can implement a multiplier. This is one example approach. So I'm going to need several registers, first of all. One that holds the multiplicand up here in register B. I'll use another register for holding the multiplier initially. And then I'm going to use another register, and in fact, this design, what I'm going to do is combine the registers A and Q down here at the bottom which at the end will hold the final result, or the product of the two numbers held in B and Q. We're going to use an ALU for doing arithmetic, an adder essentially, that adds the values up. We're going to have a control unit, or an FSM, that sets up the data path of the control signals to execute what we'd like. And we're also going to use a counter then to keep track of our iterations, or how many steps we have in our circuit. So I can describe the control for this circuit using a state diagram as we did in 133, or you may have also seen something called an algorithmic state machine, which is very similar to a state diagram, and also very similar to the way that we're going to specify flowcharts and assembly programming in the coming weeks. Rectangles in this case represent our states. The little diamonds are our decisions, and then the circles are actions, or where RTL operations can take place, as well as in the states themselves. So in this case, I'm going to start off with an initial state idle, and then a signal G, or go, will tell me when I'm actually going to start. So if the signal to go, we're going to initialize the circuit to start doing the multiplication. So we're going to set the A register, which is our sum, initially to 0, and we're going to set our counter to n-1. We have n bits we're going to multiply. There's n steps in this algorithm. Then we move on to the actual multiplication. In the first state, mul 0, is where we're going to check the least significant bit of the Q register, Q0. Remember, this is our multiplier at the beginning, what we're going to multiply the multiplicand by. If that bit's a 0, then we don't add anything to the partial sum. But if it's a 1, then we're going to add B, the multiplicand, to the current partial sum, which is held in A. And we're also going to keep track of the carry to put this into the C register. Then on the next clock cycle, we're going to move into the next state, mul 1. And in this state, what we'll do is, and this is a trick to save some logic, we're going to shift the carry into the most significant bit position of the register A, and also shift A to the right, all the bits 1 bit position, and the least significant bit of A will go into the most significant bit of Q, and all the bits of Q will also be shifted over 1 bit to the right. So essentially we're treating this as one big shift register, and that least significant bit after we've checked it in that current step falls off when we don't need it anymore. And for that reason then, after we've done this n steps, shifted n times, at the end we'll have the full partial sum in this register A and Q. And so at the end, we're going to check Z. Z in this case is detecting when our counter reaches 0. And we're going to keep doing these same two steps, same two states, until we reach 0, and then we finish the multiplication. So this is an example of how we can use RTL, as well as an algorithmic state machine, to describe a more complex circuit. And you may want to use a similar approach for the first hard work assignment where you're describing a sorting algorithm.